there about the board. How may I help?
Okay, everybody, I think it's time for us to get underway, so it's 10 after the hour. So Happy New Year, everybody, 2024. Pleased to introduce the first speaker of our first series this year, our Lectures at the Leading Edge, Professor Ning Yan, one of our own. So I always like in this lecture series to at least one or two people from the local community, U of T, the department, etc., so we can learn more about the exciting work that's going on here. Just a bit of background from Ning. Ning actually did her bachelor's degree in electronics engineering. Electrical engineer of sorts, right, who comes and sees the light and does a PhD in chemical engineering here at the University of Toronto. Ning also has several years of industrial experience. She worked in the paper industry, what's now called FP Innovations. She's worked with Xerox, for example, Xerox Research, as well as worked with Trojan Technologies, which does work in UV disinfection and things like that. So really right across the spectrum of areas from forest products through to the environment. She joined the faculty at U of T in 2001. She's a Canada Research Chair, Tier 1 in Sustainable Bioproducts. She has over 200 papers, is the Associate Editor of ACS, Sustainable Chemistry and Engineering, also is a Fellow of the Engineering Institute of Canada, the Canadian Academy of Engineering, and also the International Academy of Food Sciences. So very accomplished with a wealth of experience. I'm looking forward to hearing her tell us about building a sustainable future using bio-based chemicals and nanomaterials. Please join me in welcoming Professor Ning Yan.
Good morning. Thank you, Grant, for the very nice introduction, and thank Jay and the selection committee and allow me to have this opportunity to share our work with all of you, with our own department community, and this is a tremendous honor, and it's really wonderful. So today what I'm going to talk about is really summarize some of our recent research in this area of bio-based products. And we're all very familiar, and today is that our world, our society is confronted with some very complex grand challenges, which ranging from a very wide areas. And as a result, we have, United Nations has set up this very ambitious goal for the 17 goals to transform the world to achieve sustainable development. Among all these 17 goals, they're including climate action, clean energy, and under this context, as we are looking for ways, and as researchers are looking for innovative technologies can help us to address these challenges, and we are also, as a society, is moving towards, shifting from a fossil fuel-based economy to a more of renewable carbon-based economy. And this is partly driven by this concern about climate change, and Canada has very ambitious climate action plan by net zero in terms of the report had set up by the Canadian government. We're supposed to achieve the target of net zero by 2050. And recent United Nations conference, COP28 in Dubai, has really reached an agreement that clearly states that we are gonna, beginning of the era that we're gonna shift away from fossil fuels. And so it really calls for swift and just and equitable transition. And so these are all basically, I would say, mega trends, and set the background for as we moving towards more and more to use renewable carbon to make materials or chemicals to meet everyday challenge instead of petrochemicals. And there's another driving force. I think this chart did not show up here, and don't know why. And so that's basically as a society, we are quickly decarbonize our energy and transport system. We know that out of all the petroleum, the fossil fuel and crude oil we extracted, most of them goes to fuels and energy. Only small fraction which is used as a feedstock to make chemicals and polymers. But yet this was missing to show is that this a little bit percentage, translate to highest return, about 40% of revenue. But the problem is that this petrochemical feedstock has been, over many decades, highly optimized in cost, in process conditions. So we get a feedstock for petrochemical is quite cost competitive, very cost effective. So as we start to shift away from a demand on fossil fuel for energy and the transportation, then there is maybe resulting in less production and less availability of these, biorefinery feedstock for the petrochemical. And also maybe we change the cost structure. So all these add another layer of driving force for us to look into alternative ways to produce materials and chemicals to meet our everyday needs. So from a perspective of bio-based chemicals and bioproducts that I'm specializing in, and I think there are opportunities for us to really help with this transition. And there are multiple ways we can enhance sustainability. First one is that we can use renewable feedstock, and definitely that's what has been championed for by various initiatives under the climate action. And not only we have to use, we can use the biomass from forest and agriculture as it is. We can also use some of the waste residues, and they're all available in large quantities in countries like Canada and across the world. So there's a really large available renewable carbon allow us to use as the starting material to synthesize materials and chemicals. And of course, this is true in terms of green chemistry approach, whether we are using renewable carbon or generally making chemicals and products. But we can potentially sometimes combine the two and add the benefit and both to the environment and enhance the sustainability to use a simpler process, less harmful solvents and chemicals. Another one is that this is also a recent shift towards that concern with the waste plastics. So can we incorporate circularity in our product design, in our molecular structure, so that we can make the products originally not recyclable become recyclable to reduce our waste? So today I'm going to give you a few examples that my lab is working on among these areas, and hopefully to showcase the promise that using renewable carbon and from the biomass origin, we have opportunity to produce the materials and chemicals to meet our today's need and replace petrochemicals and have a less impact on the environment. So first I want to talk about the commodity plastics and polyurethanes. And so we know that polyurethane has a huge market share, right? So it has like $75 billion in market share in 2022, and it appears in various multiple diverse forms and shapes and meets our everyday needs. And you basically can find them in automotive, appliances, constructions, and footwear to the furnitures and the mattresses you sleep, and coatings, adhesives. I think all these synthetic leather, and you can't tell with are all polyurethanes. So basically, every day you can find these polyurethane products, and it's truly ubiquitous. And of course, there's also a big application in biomedical as well. And so this is really a commodity plastics and huge volume and huge value, and it's primarily petrochemical derived product. And the reason polyurethane is so widely used and is quite important for our daily life is because it's very, very versatile. It can be made into elastomers. It can be made into rigid or soft foams and or films. So it appears in different properties and forms and shapes that can meet our everyday needs. And if you are not familiar with polyurethane, a very quick basic primer, it's actually very simple in chemistry. It primarily consists of two of the starting monomeric material before we make polyurethane. One is a polymer which contains called isocyanate functional groups. Typically, is a diisocyanate functional group, so allow it to be polymerized. And another raw material is a polyol, basically a polymer with OH, or a molecule with OH at the end. So then this OH will react with isocyanate group, form this uracil linkage. And so this molecule or polymer, what we usually call, is polyurethane. The beauty of this polymer is that because you can really structure them to form, to adjust the hard segments and soft segments of this huge long chain molecule, so you can deliver different properties and functionalities that you want. So very similar for people who are familiar with block copolymers. So it's a bit like that. So you can adjust. You can really adjust this architect to get what the results you need. And so what we want to do is we want to, instead of make a fully petrol-based polyurethane, we want to replace either one or two the starting raw materials with a bio-based to make a bio-based polyurethanes. And so there are different, if you look at these efforts, not only my group, there's many people working in this area, including a lot of companies, chemical companies are very interested. So usually you can classify them into two approaches. One is replace polyols, because polyol is simple. I said all it requires, it has OH. And we know the biomolecules may not have other functionality, but the OH for sure is there. So it's kind of obvious. So you can use a lot of biopolymers, like cellulose, lignin, or any other starch, chitosan, whatever has OH. You can use that potentially to replace the petrol-derived polyols as one of the raw material. And another possibility is actually the isocyanates. And I'm going to talk about the third component, but isocyanates, because isocyanates, the traditional industry make it involves not only petrol-based, but uses a precursor, which is very highly toxic, like phosphagen. So to find a bio-based or bio raw material way to synthesize isocyanate instead of petrol has an added advantage. So this is a lesser approach in this area. So my group looked in these both approaches. So first I want to share with you the work we have done as example to make fully bio-based polyurethanes. And in this case, all the raw materials are bio-derived. And that involves that I'm going to show you how we synthesize different components eventually to make this new fully bio-based polyurethane. And we are targeting a special type of polyurethane, which is higher in functionality called shape memory films. And to review, I mentioned when we make polyurethanes, we need diisocyanate, we need a polyol. But in many cases, because we want to structure this molecular architect, we usually add a chain extender to allow us to adjust the soft region and the rigid region, and so to produce the materials that we want. And the first work I'm going to share with you as example is, first we want to synthesize a bio-derived isocyanate. And in this particular work, we used a raw material called abiotic acid. So abiotic acid is a biomolecule you can find in tree resins. When the pine tree sees those resin come out, part of the rosin, a major part of the rosin composition is abiotic acid. You can also get industrial-wise from tall oil and in the pulp and paper operation as a byproduct as well. But usually it appears in some sort of isomer form, but it has one carboxyl groups. So to make a difunctional isocyanate, we took a dimerization approach. We first dimerized the abiotic acid. So now we have a difunctional groups. Then we, through Curtis rearrangements, we make a diisocyanate from abiotic acid as the starting material. And the second one is the chain extender. And for chain extender, and we also, there was no, when we did this work, there's no bio-derived chain extenders. So we took vanillin as a starting point, where if you like ice cream, definitely like the vanillin flavor. So it's very safe, benign biomolecule. It can be, of course, obtained from plants, but also could be a degradation product from lignin, from the commercial wide. So similarly, we take approach, we make a divanillin, and then we basically form a cross-linker with amino acid called ananinol. So this is the new bio-based cross-linker that we have. So if you come back, when we make polyurethane, we need this minimum two, but usually three components. We have the diisocyanates from abiotic acid. We have the bio-derived cross-linker. We need the polyol. In this case, we did not synthesize a polyol. We took a polycaprolactone diol as the polyol. The reason for that, as I mentioned earlier, there are so many available biomolecule can be used for polyol. And polycaprolactam can be derived in biosource as well, so we just use as example. We really no need to specially synthesize them. So then you can form different formulation, depends on how many, molar ratio between the three components. You can get different these polyurethane materials and of different thermal property, glass transition, cross-linking density, and as well. So this product, the goal is to form not only polyurethane, but it's a shape memory material. So this is what we get, and one of the optimized formulation, what we get is that you can, they definitely possess very good shape memory properties, means that this material, you can fix its shape under heat and pressure, and then you will recover to its original shape just by temperature, by heat, by remove heat, by apply heat. No need pressure anymore. So you have different pathways, you can basically go back and forth in this. This is like a flower, you can open and close, and it's nice to demonstrate its shape memory abilities. And in fact, if you see that the cycle, you can repeatedly to shape, fix the shape and recover it. You can see the fixation rate is very high, almost about 99%. And the recovery rate is also very high, and it's close to 98%. So you can repeatedly fix and recover, fix and recover. So excellent shape memory performances. So these fully bio-based polyurethane product, and first the mechanical properties is very good. And if you look at basically its stress strain curve, and it's fairly elastomeric. This is a strain, so very deformable. With different formulation, you get different strengths, so they retain the elastomeric properties. And also, it also has this ability to hydrolytic degrade. So, and this is what we think that the biomolecule building block allow us to add more ability to degrade these plastic products. So what this study has shown us is that not only we can make a fully bio-based product, replace petrochemicals, but also we can have comparable, perform functional performance. Then we can also have added advantage of some added degradability where we want for the product. So this replacement is not just purely straight replacement, but maybe we have enhancements. So I think this shows that the promise that we can use the bioproducts and to shift away from fossil fuel. The second example I want to give you is really bio-based polyol replacement with the lignin. And in this particular application, we are looking at make a foam, polyurethane foam, bio-based. But target one particular application is to remove the oil spill, the crude oil spill. We know when the crude oil spills, and it's really catastrophic to aquatic life. And typically cleanup is usually absorbance is one of the typical methods to clean up unwanted waste oil. And absorbance works very well for light fraction of oil because they can pick them away. But the fraction which is very hard to remove is the heavy crude because they are very viscous. They are gluey. They don't have flow characteristics. When you put absorbent, they don't flow into the capillary and being picked away. So this is the typical challenge in cleanup, that is the heavy crude fraction. Sometimes the absorbent is very ineffective. So what we want to do is we want to make a bio-based absorbent and take advantage of a very simple idea that everybody knows, that when you do cooking, if you use this butter, you heat up oil, the butter starts to flow. So we know that typically oil and a lot of this heavy crude, if you raise temperature, viscosity drops and become able to flow. So very simple idea. So what we did was that you take the lignin, you liquefy them, and then make a bio-based polyol, you react with diisocyanate, form of foam. And the ways we want to do it is not only we want to form a bio-based polyurethane foam, we want to also utilize the ability of lignin has this photothermal effect. It can absorb sunlight and convert to heat. And so that we can raise the temperature of the absorbent, the surface. And then when this absorbent surface come in contact with the heavy crude oil, and the oil temperature raises and drops viscosity, start to flow and being picked up. So this is what we try to do. And to do this, not only we want to rely on the lignin, we also try to load up additional filler in this carbon nanotube to help with this photothermal conversion. So if you look at this lignin-based foam in terms of absorption spectrum across all wavelengths, you can see without loading carbon nanotube, like lignin, most absorption happen in the UV, a little bit near infrared or infrared range. Visible light is very low. When you load up a little bit carbon nanotube, this absorption is very good across whole broad spectra. And if you look at the photothermal effect, and so this zero means there's no carbon nanotube, there's 30% of lignin in this formulation. And you can see under the simulated sunlight, and very quickly the surface temperature can rise, and can rise to about 70 Celsius in a few minutes. So what happens is that these adsorbents floats on the surface of water on the sunlight, absorb the sunlight, convert to heat, and this heat from the surface will conduct through the foam absorbents and in contact with the crude oil, and hopefully can suck up like a sponge the oil. And if you look at the water contact angle, and we really don't want we want a very high water contact angle. We want the water doesn't really penetrate inside too much. And so with the nanotube also helps a little bit further increase the already very high water contact angle, sometimes can reach super hydrophobic. And in terms of oil, you can see at 40 degrees C, if you put a drop of oil on these absorbents, and you can see that this heavy crude oil doesn't really penetrate. After 10 hours, it still stays on the surface because the flow characteristic really is not there. If you slightly heat up a little bit, you can see very quickly it can go in. So there's a bit of echoing. Okay, so if you look at these absorbents and you put into the crude oil the black gooey stuff at the bottom, you put the absorbent on top, you turn on the simulated light, and you can see that temperature start to rise. At 4 minutes, reaches 74 Celsius. And after 6 minutes, you remove this absorbent, the water is clean, all the oil picked up. If you don't turn on the sunlight, it's low light, nothing happens, no flow characteristic, the oil retains. So you can see that, and because this lignin-based polyurethane has very high mechanical properties in terms of as a foam, in terms of elastomeric properties, you can see that it has very low hysteresis. Basically, you can take this foam, you can squeeze them, it will return back to the original shape. So you can, after absorbed oil, you can squeeze out the oil, you can reuse again and reuse again, so repetitively. So you can see that basically you can take the oil and recover them and again many, many times, almost at no reduction in performance, except at the beginning, the first time the surface has a little bit of absorption. So this is very effective, so you can basically recover all the oil and keep using them. And another advantage of using lignin-based raw material to make polyurethane is that before these polyurethane, after adsorbents, after end of life, it's landfill. There's no good way of dispose them, or maybe incineration, but it's very low in density. So once you use the lignin, you have another alternative way to decompose them because the lignin breaks down in alkaline solutions. You can potentially break them down and reuse them in a chemical way and to prevent the secondary pollution. So this is the bio-based product. Not only can have high performance, being smart, but also can have less impact on the environment, way better than potential petrol alternatives. So that's one example on the polyurethane. I want to switch gear on the second area that we worked a lot, I think my group, on this nanomaterial in the cellulose fibril. We know that biomass, especially plant or trees, they have this structure hierarchy, means that the main composition of, like for example, wood is from cellulose, hemicellulose, and lignin. Cellulose is really the load-bearing building block that forms, they kind of hierarchically arrange themselves into the cells and the fibrillar cells. They form the elementary fiber and the bundle eventually from the wood trunk form the tree. So there's a lot of work recently and try to basically go reverse. And so we want to get the cellulose down to the nanoscale. And there's quite a bit of research in this area using nanocellulose. And nanocellulose has mainly two types. One is to take cellulose, the microfibrils or the bundles, and remove all the amorphous region. left with only crystalline cellulose. They are about 100 nanometer in diameter, in length, 10 nanometer in diameter. So they're needle-like. Another way is just take these fibers and mechanically grind them, make nanofibrillate them. So they are very long. They are kind of like a bit messy, but the diameter is in the 10, 20, or 30 nanometer range. So there are two types of nanocellulose fibril or crystalline cellulose. And so if you go to literature, there's a huge body of literature because nanocellulose is very different from the normal cellulose fiber you see in paper because they have a lot of special attributes. They appear as a gel with a small concentration, and they have very high strength, and their strength is like to weight ratio is 8 times higher than steel. So they are high aspect ratio, especially in the fibrils. They have high surface area, and so they can use the very wide range of applications. And my group also worked a lot on both type of nanocellulose, for example. And here we can make cellulose aerogels. And this is highly structured and oriented. And you can also carbonize the aerogel, make the electrodes. And you can potentially use the scaffold form photocatalyst. You can also utilize its chiropneumatic structure to form the sensors based on the optical properties, and also temperature sensors through the hydrogel. So you can make a variety of these kind of products. But today what I want to share with you is a very unique product come from my lab called lignin-containing cellulose fibrils. So before our work, most people in the literature only work with pure cellulose, means that the lignin has to be removed. And what we came up with is this new type of cellulose fibril with most of the lignin retained, larger than 20% of lignin. So that's why it's kind of brownish compared to the pure cellulose. We felt there's a lot of advantage compared to the pure cellulose fibril. First, we have higher yield. We don't need to remove lignin. Second, we can retain the lignin advantage, which is more hydrophobic, more thermally stable, and UV absorbing. And so many other functionality we can utilize from the lignin. And so that we can overcome some application where cellulose fibril, pure cellulose fibril, is too hydrophilic and cannot form a very good interface with polymeric substances where typically hydrophobic. So now we have this lignin intact, and so we hope that we can open up a lot more advanced applications that the pure cellulose fibril cannot do. And this work came out as a kind of a serendipity. In our many years, I worked in the area people may familiar in the bark utilization, tree barks, as a waste residue. So we took the tree bark and we take a very simple caustic extraction. We take the polyphenols, and we use these polyphenols to form the bio-based epoxy and bio-based polyurethanes, and also PF adhesives. When we took out these polyphenols, this is what it looked like. We have a huge fraction which remained as a solid residue in this extraction process. And this is primarily consists of lignin and cellulose. So what we decided is maybe we can use this as a feedstock to make this special new type of nanocellulose fibrils through a mechanical way. And we can return the lignin content and still obtain this new type of nano materials. So since we first pioneered this new type of nanocellulose fibril, and since then we are the first group to demonstrate when you retain the lignin in the surface of cellulose fibril, you will form a very nice compatibility with polymer, with hydrophobic polymer matrices. So you can apply them in whether thermoset polymers or thermoplastic polymers without need of adding coupling agent or surface modifying agent, using the existing lignin as a natural existing compatibilizer. And we demonstrate that you can add into drop-in addition into adhesives to increase performance or coatings. And recently we have shown that because lignin contains this quinolic group, which are redox active, so you can actually use that as a potential flexible electrodes for energy storage applications. And so truly, our group is the first group to show this very nice synergy of between lignin and cellulose and retain in the cellulose fibril, that we really can do a lot of, make a lot of functional materials. So the production is very simple. I mentioned that you take a caustic in the waste residue, And because this caustic extraction, the phenols can still go to make the chemicals. The residues is primarily a simple mechanical grinding. During the extraction process, you create some defects in the cell wall. So as a result, it reduces energy demand in the nanofibrillation process. So it's a double added benefit. And as a result, also, this material can be easily nanofibrillated and to achieve the nanocellulose that we want in terms of morphology and surface area. So if you look at the composition, it definitely has more than 20% of lignin retained. And if you look at through the structure chemical analysis, you can see that the lignin is retained its original form that still exists in the beta-O4 linkages. And also there are intact cellulose, the lignin carbohydrate complex exists and still means that this lignin, many of the lignin, just like in the cell wall, still chemically bonded to the cellulose in this cellulose fibrils. And indeed, when you retain the lignin, lots of lignin on the cellulose fibril compared to the pure cellulose fibril, you get a higher thermostability. You get a better water stability because the pure cellulose, if you soak in water, films after 48 hours, it becomes kind of open up, have no structural integrity. And if you retain the lignin, after 48 hours, it still has some structural integrity. And we have shown that, for example, you can use as a reinforcement for composite application. And using cellulose fibril for composite application is one of the biggest promising applications for automotive, for packaging, to replace plastics. But for example, the polylactic acid is a biodegradable polymer. And one of the challenges is its performance. And it does not have high barrier properties. It tends to have low in terms of mechanic performance compared to many engineering plastics. So there's many at work try to reinforce polylactic acid to make it more applicable for various applications. And efforts to try to use the cellulose fibril, nanocellulose, has always failed if there's no chemical modification of the fibril or adding additional coupling agent, because PLA is highly hydrophobic and cellulose is highly hydrophilic. So it's like oil and water doesn't mix. You don't create a strong interface. You never can achieve a very good product unless you chemically modify it. So we show that if you mix this fibril without chemical treatment, because of lignin on the surface, and right away, you can, even adding 5% or 10%, you start seeing enhancement in mechanical properties. And also you see the enhancement in barrier properties means that this is the water vapor transmission rate. You can see reduction. So you can see that these can be more suitable, very suitable for making as a packaging material, biodegradable packaging material, replace plastics. And before we report these results, nobody in the literature have shown that you can just drop in cellulose and without compartmentalizer or modification, get enhancement in mechanical properties. So clearly, this lignin retention has a lot of advantage. And similarly, you can demonstrate in the thermoset, in the epoxy, and this, you can have the cellulose making the film, and together with the epoxy from the composites, you can see the strength is definitely enhanced, but not only enhanced, it's higher than individual components. And typically we say we make composites, the mechanical property fall in between. But yet this one is even more than individual properties. That means there are some chemical reaction synergy occurred. And also if you look at the water vapor transmission rate, it's even better than epoxy film itself. So that means this, once the lignin with its aromatic backbone structure is very compatible with epoxy thermosets, and you really can use it to make very high performance composites. And so you can also use for energy storage application and utilize this quinonic group and make the flexible electrodes. And so to have, I want to speed up a little bit, and high performance in capacitance compared to all the literature research. And more recently, we worked into this tribal electrical nanogenerator. And nanogenerator means that you can turn mechanical motion into electricity and utilize tribal electrical effect. We all had this experience when you rub the comb of the hair, you generate static charge. So this, you can take advantage of those charge transfer between two materials and generate electricity. So you can have different modes. You can slide in, you have contact. And you can have many applications. For example, you can harvest your walking and tapping and make the contact to create electricity. You can utilize your breathing and heartbeats to generate electricity power detector or reporter. You can even harvest the wind and waves, tidal waves. And also through the raindrops, when you flow through a substrate, you can also generate power. And for example, we have done collaborating with Professor Golovan's lab in MIE. We create these different patterns allow us to harvest water from the mist and generate electricity and hopefully to power to be able to simultaneously capture water and energy suitable for greenhouse applications. And one thing I want to show is that for these new type of fibril, we have demonstrated a very exciting discovery. Because when you make this contact or this kind of tribal nano generators, typically you need to pair something which is very electropositive, tribal electropositive with electronegative. And we have a lot of natural materials and naturally electropositive, means they, but yet the electronegative, the most common standard is the PTFE Teflon. And this is a synthetic petropolymer. And what we do is when we pair them with different electropositive material from metals to relatively less electropositive from the pair against the Teflon, the LCNF shows higher performance, whether in generated power in terms of voltage and current, means that they tend to exhibit even more electronegative characteristics. So the more the difference between the two layers in tribal positive and negative polarity, the higher electricity you can produce. So this we can see that across different substrates, different pair, we always show consistently higher than Teflon. So this type of device usually is for wearable electronics, so we want to make it more environmental friendly. And we usually don't have a very good option in a natural material for the electronegative layer. So it's the first time we show a natural material without modification can acting as a negative layer for this tribal nano generator and has higher performance than the gold standard Teflon. So I think this is very exciting, and the power is so high, you can form this stacking and tapping to charge the capacity, the power circuitry that able to see the signal which is picked up by the cell phone. So. Lastly, I want to quickly wrap up the recent work we are working on in address these plastic waste issues. We know we all have a concern about the waste plastics that we don't really utilize them much. And there's two types, usually plastics. We have the typical familiar with the plastics where you can heat them up, they will melt. In theory, from a chemistry perspective, they can be recycled, but we have an issue with collection and mixed material that they don't get utilized. But we also have a group of thermoset polymers, which by its material nature, they cannot be recycled. Means that when you heat them up, they don't melt. If you heat up more, they degrade. So the only way is landfill or combustion. So they don't have very good disposal, like epoxy, like the windmill turbine, there are a lot of sports goods, cars. They are purely just waste. So what we are trying to do nowadays is to incorporate some dynamic bonds, covalent adaptive dynamic bonds into these network polymers so that under external stimuli, these bonds can break and reform. And typically, there are many different types of bonds you can utilize. And for example, there's disulfide bonds and or imide bond or transesterification or metal coordination bonds. And one of the work that Nicole, she's here and she's done, has a PhD thesis, is to incorporate these dynamic bonds, and especially disulfide bond, into the starch-based epoxy and build on her work that previously made the starch epoxy replace bisphenol A. She used a disulfide compound instead of a petrochemical. So we have a starch as the starting material to make epoxy. We take a disulfide from a garlic. So then we have a more bio-based material. This disulfide bond is what responsible why some people have curly hair and some have straight hair, or you can perm your hair. So it's the same idea. You can restructure the bond. And so what happens is that this material, this is where the starch epoxy incorporate the disulfide bond, And after usage, you can grind them in powder. You can, under heat and pressure, they can reform them again. And if you look at the performance, you can see that they can, basically form the product, grind in powder, form it again, and while you're doing this repeated remodeling cycle, the material gets stronger and stronger. So this is very interesting. Not only you can recycle, but also you can upcycling instead of down cycle. And typically, when you report this kind of result in the literature, maximum you can recover is 100% property, but now you get stronger and stronger. So this is a very interesting result. And with all vitrimers at the end of the life, you can chemically decompose them into polymers and close loop recycle them chemically. And so lastly, I want to quickly, because of time, you can do the same with lignin polyurethanes, but utilize metal coordination bonds. And similarly, because you incorporate these metal coordination bonds and utilize the lignin in the photothermal effect, not only you can, you can make this bond quickly exchange under its optical illumination, they can self-heal, and also you can fully recover its mechanical properties, and also you can have very simple closed-loop recycling with this zinc as a catalyst. In this case, that basically you can decompose them into small molecules and reform them, fully recover its original properties. And similarly, you can use other feedstock like chitosan to do the same work. So I think that was a little bit rush at the end, but clearly that the work that many students are working on is to utilize this ability to incorporate restructured bonds into the original thermoset material, make them recyclable, reduce plastic waste. So lastly, I want to acknowledge the funding agencies and from various organizations, collaborators, that their work has incorporated in today's talk. And Dr. Chen, we had the China Calendar Collaboration Project, and she stayed in my lab. And also Professor Karen Liang of MSE, and Professor Golowan at MIE, and Professor Bang at Waterloo, and many industry partners. Lastly, and the most importantly, my group members and the student postdocs, and they have done all the work. And thank you all for attending.
Thank you, Ning. Very excellent talk. A wide range of areas that you're working on connected to biomaterials. So we do have time for questions. So questions.
Well, Professor, I'm really happy to hear your excellent presentation. And I have two questions. The first question is about the engineering. Because just now I saw that your presentation on the material is derived from the bio-based material. I really want to know if this system of your production, the boundary is from the raw material directly from the biomass or from the molecule derived from the resource of the biomass. I think it's really necessary to conduct the analysis from the cradle to gate, because in this process, especially for the biorefinery, we have to know if we input some energy and what this energy is from. So we could call that is energy effective. This one is about engineering, and another one is about the science. And I'm not sure this process is about the catalytic process and how to use the catalyst to control the selectivity, because especially for some different hydroxyl group in the material, and you have to use the catalyst to control the different reactions. For example, the hydrogenalysis or dehydrogenation or something else. Yes.
That's a very good question. Okay, so the first question about engineering, so-called life cycle analysis. And of course, first of all, if I were to conduct, the life cycle analysis, this will be a comparative life cycle analysis because we have replaced petrol products, right? So definitely from cradle to to grave, and we will have to come from the extraction starting. But generally speaking, the reason shift from fossil fuel to renewable carbon is that the generally life cycle analysis has shown that the carbon extracted from the biomass typically can have a less impact, if it's not carbon neutral, but less impact with fossil fuel extraction. So I have not done life cycle analysis myself, specifically for the product, but there's many, many research out there and talk about that. Of course, on the other hand, in terms of the process itself, and if this product is the comparative usage, is a replace existing, then the downstream impact, it will come from disposal. I mean, shipping is the same, usage is the same, or maybe how long it's going to use the same. So I think, I totally agree. For these material to really justify its environmental benefits, a whole system-wide life cycle analysis is necessary. But so far, all the indication has indicated that it's more favorable. Once we have this product in place, and I think there are many examples as such, but I totally agree, whatever we do, we should look in from a system level. The second, in terms of catalytic reaction, so what I showed is a very wide range. And some of them, it's catalyst-free. For example, fully bio-based polyurethane. We use the one-part synthesized without catalyst. That was one aspect in the green chemistry embedded in that conversion. But later on, in some of these Vitromer work, we do have catalysts used. And it's not, sometimes the catalyst is not really for the hydroxyl, but it's more triggered ring opening or stuff like that. So definitely there will be some careful selection in those conversions.
Other questions? We still have time for other questions.
Hi, Professor. Thank you so much for this talk. It was very amazing. I have two questions. So one, you showed that LNCFs, they can conduct electricity because of their positive and negative properties sandwiched together. So one, is motion the thing that allows it to keep moving electricity? And the second question is, since you've proven some of the benefits and applications of these bio-based materials, what would the next steps and the path to commercialization look like?
Yeah, so the first question I want to clarify, so this material is not electrically conducting. They are insulating material. The reason I say that because they have this quinonic group, because they retain the natural lignin structure, and they are redox capable, but they are not conducting electricity. So because they have redox abilities, when you apply them for electrochemical applications, they can potentially participate in those electrochemical reactions. What you are referring to is the tribal nano generator, where you have multi-layers, where you have electropositive, electronegative layer. When they in contact or in friction, they promote static charge exchange, charge transfer. In this case, we felt is because the lignin retained on the surface, where it has some unique structure that allows some kind of pi-pi transfer, but exactly mechanism, we don't really know. But that's why it's a very interesting discovery that we found this new material has high performance and capable of, beating the Teflon as the gold standard. In terms of the commercialization, that's a very good question. The biggest challenge for the biomass work is that to replace petrochemical, their starting costing prices tend to be a bit higher. So we have worked in the company, gone through some, pilot plant and large scale trial. I have not have anything which is directly commercialized, but in this bark area, I think we are talking for another company still actually pursue or construct, hopefully, some bark biorefinery. And this comes from not only the challenge of the cost structure, but also the companies before lacked a bit driver because when the oil price go up and everybody want to change, when oil price go down, everybody disappears. So it's like cyclic. So I hope with this recent trend in the COP and all these government policy drivers, we will see some more committed investment and collaboration partnership.